All right, so now that we've gone through Lewis structures and we know how, with this theory that is based on octet theory, right, we know how to come up with reasonable connectivities of atoms that are reflective of their bonding properties. What we're going to do next is we're going to use a VSEPR to predict the structure of molecules. So this is just an extension of octet theory and Lewis theories. VSEPR stands for valence shell electron pair repulsion theory. And this is because the theory is all about electron-electron repulsion, as we'll see. This is a remarkable theory in that it works very well and is extremely simple. This is why it's great for general chemistry courses, right? The problem is that it's completely empirical. So what does that mean? That's completely empirical. That means it's not really founded in anything more fundamental other than pattern recognition. So, people looked at the structure of a bunch of different molecules, and they looked at their Lewis structures, right? The crystal structures, their actual structures, and their Lewis structures, and then they came up with, they saw some patterns, and so they came up with these rules. And so it's really remarkable that this works so well. Because it's empirical, not based on anything sort of any deeper principles, it is wrong. And we'll see many times where it fails. And when I say wrong, that's an interesting word, right? What does wrong mean in this context, in kind of the bigger context of science? Um, it's just not a good reflection of reality. Okay, it's a model, just like everything else we have. Quantum mechanics is a model. I don't think we really know at a very deep level what anything is, right? We're trying to figure that out, but we come up with models. We come up with theories. That's what theories are. That that better and better reflect reality as we observe it with our senses and with instrumentation. And that's really, a core principle of science. So VSEPR is just a model that we know is a relatively poor reflection of reality. Okay. And this is because we know quantum mechanics is closer to the truth. Okay. Um, and so just keep that in mind. We'll later in this chapter go over molecular orbital theory, which is based on quantum mechanics. And that will allow us to predict the structure of molecules and many other properties with much better accuracy. Problem is that it's a much more complicated theory and requires a lot more background information and calculations to do. But that's okay. It's a better theory. Anyway, so VSEPR is all about electron pairs being bonding or non-bonding and repelling each other. Non-bonding electrons are called lone pairs, just like in Lewis structures. And there's something we're going to invoke here called the steric number, which is the number of ligands plus number of lone pairs. When I mean ligands here, I mean distinct chemical species that have distinct bonding sites. So you can kind of think about it as number of bonding sites. It's not number of bonds. So like a double bond doesn't count as 2. A double bond would count as 1. But 2 single bonds would count as 2, or 2 double bonds would count as 2, or 1 double, 1 triple, 1 double would count as 3 different bonding sites. And it's always to a central atom that we're talking about. So we'll talk about the VSEPR geometry around a central atom. If you do have an odd number of electrons in your species, we're going to treat the single unpaired electron in the same way, basically, as a lone pair. And the whole premise of this theory is that electrons want to repel each other. So non-bonding electrons want to repel other non-bonding electrons, and bonding electrons want to repel other bonding electrons, and they want to repel each other. Okay, and they're going to do this by maximizing their distance from one another. And so remember, you not only do you have lone pairs, but you have electrons in the orbitals that are participating with bonding. So VSEPR uses different steric geometries depending upon the steric number. And so here is for steric number 2, you have a linear setup that gets these atoms as far in their electron clouds or their orbitals, right, as far apart from one another as possible. That gives an idealized bonding of 180 degrees. And with steric number 3, when you have 3 things, okay, attached to a central atom, be it lone pairs or atoms, that's going to be a trigonal planar structure. So it's basically a triangle, which is why you get 120 degrees, 360 divided by 3. That's the maximum distance you can put things. Now, what does it mean, idealized bond angle? Well, a lot of times you will get a lower bond angle in actuality if you have a lone pair. Actually, you always will if you have a lone pair. And the reason is this lone pair VSEPR says that it takes up more space. Okay, what does that actually mean? I don't know. This is just part of the theory. Okay, so this is just kind of an artificial thing of the theory to make the data fit. But if you have a lone pair, the angle will be less than 120 degrees. What will it be? You have no way of knowing. Okay, the theory doesn't tell you go any deeper than that, but you know it will be less than 120 degrees. And that will basically, because it's going to take up more space and cause the other, that cause the atoms, the angles with the atoms to contract. Okay, because the angle with the lone pair, which we usually don't talk about the angle with the lone pair because where are the electrons, you know, it's Heisenberg uncertainty principle and all this, but we do know where the atoms are. Those angles with the lone pairs are going to get bigger. Okay. Tetrahedral, steric number 4, 109.5. It's not just 360 divided by 4 because remember you're in three-dimensional space, and so geometry dictates, three-dimensional geometry dictates that 109.5 and a tetrahedron are the best ways. It's the only way that you can put 4 points in space and have them as far apart from one another as possible. Trigonal bipyramidal is 5. Steric number 6 is octahedral. And a pentagon, 7. You may not have seen this before, pentagonal bipyramidal. And if you look at this, there's basically this is a pentagon, okay, in here. And then there's 2 pyramids. So let me just redraw that so you can see that. So it's coordination number 7 here, or steric number 7. And so there's a pentagon in the so-called equatorial site. Why is the bond angle in there 72? Well, that is 360 over 5, right? But then these angles here with the axial sites, those are 90 degrees, those are right angle. And so you end up with a pyramid, right? A bipyramid, looking like that. And one again on the bottom, looking like that. Very similar to the trigonal bipyramidal, right? Where you have a triangle, and then you have a pyramid on top, okay? And you have a pyramid on bottom, hence the bipyramid, right? Square antiprismatic, that one's kind of interesting. There's actually 3 different bond angles. And you can go beyond steric number 8, but we're not really going to get into that. They're increasingly rare type of molecules. One thing I do want to point out, a source of confusion, I think, for a lot of people is, well, why is this called octahedral when the steric number is 6? Shouldn't it be hexa something? Well, it's because 6 points, there are 6 points here, right? There's the steric number 6 terminal atoms in this picture. But it's because the number of faces, okay, hedron, right? Hedron means faces. The number of faces is actually 8. So if you count up all these triangle faces, okay, there's one there, another one here, that's 3, and then one in the back, 4, and then there's equivalent 4 on the bottom side, so there's 8. All right, so let's do an example. How would we predict the VSEPR geometry of this molecule, the xenon molecule? Well, first we're going to have to start by figuring out the Lewis structure. So start by figuring out the number of valence electrons. We have 8 valence electrons for xenon since it's a noble gas, 6 for oxygen since it's a chalcogen, and 7 for fluorine since it's a halogen. Times that by 4 because there's 4 of them. And that gets you with 8 plus 6 is 14 plus 28 is what, 42? Good. And so xenon is going to be our central atom. And now we don't really know what the geometry is, but we're just going to kind of put these in a pentagon, okay, for now, because we don't know what the steric number is. That's why we're doing the Lewis structure, to figure out the steric number, figure out the VSEPR geometry. So we'll just arbitrarily connect all these right now. We have 42 valence electrons. We're going to give everything the octet rule, all the terminal atoms the octet rule, and see what happens, right? Because we know we have to satisfy the octet rule at least as much as we can. And what happens here? So now all the atoms are, well, all the non-central atoms, the terminal atoms, are satisfying the octet rule. Xenon's already violating it, but we know it can have an expanded octet because it's 2, 4, 6, 8, 10 valence electrons. But the other ones, the terminal atoms, all have the octet rule 2, 4, 6, 8, and there's 5 of them. I've all driven them with the same sort of electron configuration. So 5 times 8 is 40. So that means I have 2 more electrons to be accounted for. So I could draw the structure like that, right? So how does this look? Well, this is telling us that we have one lone pair around the central atom. We're trying to figure out the VSEPR geometry here. And we have five ligands, right? So our steric number is going to be 6. Steric number. So this means we're going to be, our steric geometry is going to be octahedral, based on the octahedron, based on that table that we went over on the previous slide. But we're going to be removing one of those 6 points is not going to have an atom. And so that is octahedron shape with one of the points removed. So it's going to be a square pyramidal shape. And indeed, that's true. Here this says 5 ligands plus 1 lone pair. Octahedral arrangement. Okay, so square pyramidal, right? You'll see in this diagram here, I actually have a double bond bonded to the oxygen. And so why is that? Let me just get that out of the way. The key thing here is we correctly came up that square pyramidal. It's just our Lewis structure isn't the best that it could be. And so what you can do is you can bring a lone pair down, okay? And now you still have the same number of electrons, right? You still have a lone pair there. Everything else is the same here. There we go. But why would this structure be better with a double bond? That we have to think about formal charges, right? And so let's calculate the formal charge. Halogen for F is 7 valence electrons minus the 6 electrons that are non-bonding. 7 minus 6 is 1 minus half of the electrons in the bond. So 1 minus 1, because there's 2 electrons here, half that's 1. 1 minus 1. So this is 0. So all these fluorines are the same, so there's 0. And we didn't change that up here, okay? Here, however, we have oxygen has a formal charge formula. Oxygen has 6 valence electrons minus minus 6 non-bonding electrons minus half of the bonding electrons. So minus 1, we have 1 bond. So that gets -1, okay? And what is xenon? Xenon here is, well, xenon is 8 valence electrons, and it has 2 electrons in lone pairs, and then it has 1, 2, 3, 4, 5 bonds. So that is +1, okay? But look what happens when you do it here. On this side of things for oxygen and xenon, we can do the same thing. Oxygen here is going to be 6 minus 4 minus 2, right? 4 non-bonding electrons and 2 half of the bonding electrons, which is 0. And xenon is going to be 8 minus 2 minus 6 bonds equals 0. So all the formal charges are 0, so hence you want this one. You know, you could experiment with making things like this, double bond to fluorine. That is a resonance structure, but it's not going to be favorable, because in that case, you have some bonding motif, a double bond to fluorine. And if you do that, what is the formal charge going to be? It's going to be 7 minus 4 minus 2 7 minus 4 minus 2, which is 1. And halogens, especially fluorine, never want to have double bonds with them because of this, because the formal charge is positive. Remember, if you have to have a negative somewhere, you want it to be on an electropositive atom. And fluorine is the most electronegative atom. It really doesn't want to donate its electrons away. I mean, that's what you're doing here when you're making a double bond. You're saying, hey, I'm going to share more electrons. I'll share more electrons. No, that's not going to happen with fluorine.